Good afternoon.
Good afternoon.
Good afternoon. We are open. Good afternoon. 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 Good afternoon.
How are you?
I'm very well, thank you. And yourself?
Not too bad.
Good. Good afternoon. 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 Good afternoon.
I want to put my stuff down, go to the toilet and come back. Is that okay?
Do I need to know that?
Yeah, I feel like you might look at me weird if I don't come back.
No. Good afternoon. 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 Good afternoon.
Afternoon.
Good afternoon.
Hello.
Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon.
And then it's a matter of like seeing how you do it.
Good afternoon. 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 Okay, ladies and jelly beans, let's make a start. The sooner we start, the sooner we can go home. Just because I've been asked by some people, you probably have noted that there are no attendance sheets in these workshops. The reason for that is very simple, because I honestly don't know or don't really care where you do the work, whether you do the lecture work or whether you do self-studies or something like that. So, you know, and if the stuff that we are doing in these lecture stroke workshops is totally familiar to you, then, I mean, what's the point in coming, really? That's also the reason why I send out this email on Fridays, usually, with giving you a plan for the following week with the topics, so that you then can decide, do I want to come to the workshop or not? So it's entirely up to you. In my opinion, you are all adults and you are perfectly capable of deciding whether you want to come or not. The last thing that I want to do is bore you. Okay? So for today's session, the first one, I want to very briefly discuss with you the topic of spectrophotometry, because that is a tool and a technique that you will use very, very frequently. And I think you have used it already for the DNA analysis for the kiwi fruit, right? You've used the spectrophotometers. Is that right? Yeah. So you are familiar with the machine. Have you done the theory, the background to it as well? The Beer-Lambert Law? No? Excellent. So that's something that's pretty new to you then. And again, that is something that, I would expect a good bioscientist to do basically in their sleep. That's a fundamental of biosciences, that you understand what you're actually doing when you are dealing with a spec. And so first of all, I think you're all only too familiar with a picture of the spectrum. So we are looking at the electromagnetic spectrum here. And you are all familiar with the dual nature of, for example, light or any electromagnetic wave, that it's sort of light can be two things. It can be a wave or it can be a particle. And the distinction is sort of fluid. What we can really define very nicely is a sort of a spectrum of, if you like, wavelengths. So, for example, here you've got the oops, that's a little bit thick. You've got the spectrum of visible light, and usually this spectrum goes from a wavelength of 400 nanometers to 700 nanometers. At least this is the spectrum that humans can recognize, that humans can see. For other organisms, it is different. So, for example, what would be the spectrum that bees can see? Yep, you're absolutely right. Bees can see more into this region here, into the ultraviolet range. And you can do some really, really cool experiments if you get a sort of an ultraviolet lamp. Or they were really in the 80s and 90s in discos, where they had the black light basically, and anything that had any sort of special washing powder whitener in it that would strongly glow in this light. So it was quite funny if you had, for example, this particular underwear, it would glow through your normal clothes, and that's quite cool. But if you have one of these lamps and you shine it on, for example, some particular flowers, what you see is that the picture totally changes. And what looked like a pretty dull flower is actually incredibly sophisticated and intricate, with all the ultraviolet colors in it, which very often sort of are almost like a landing strip that leads the bee to where the goodies are. And the bees can see that, we can't. What is the spectrum that a dog can see? Just out of interest? A dog? What's the spectrum that a dog can see? Dogs can't see colors. So for them, there is no spectrum. Poor sorts. What about cats? Can cats see colors? Yeah? Yes, you're right. Cats can see colors, can see colors pretty much like humans, although they are much more diffuse, the colors. They are not as crisp as we can see it. And that was actually found only a couple of years ago, that cats can see colors. But they can see pretty well close up to about 10, 15 meters, But anything that goes beyond that, it's really blurry. So cats are not very good when it comes to looking into the distance. Mind you, they probably don't have to, because their natural thing is to catch mice, and the mice are usually in front of them. So that's not a problem. But the visual spectrum is only a very, very small part of the electromagnetic spectrum. You see, actually, that's this bit here, this little dot here. But we have got a far wider range of the electromagnetic spectrum, which goes from high energy gamma rays and gamma bursts, which are incredibly rich in energy, to very, very long radio waves. And we measure these, the spectrum usually in terms of wavelengths. And the wavelengths can be from fractions of a nanometer, so 10 to the minus 9 meter, to 100 meters, and even longer, up to, well, basically, you name it, hundreds, thousands of kilometers, the wavelengths of these. And according to every wavelength, you also have associated with it a specific energy. So each wavelength that you have has a particular energy level associated with it. Now here is something quite interesting. When I said we see colors, what do I mean by that? Why do we see color? Why, for example, is your top red? Why do we see it as red? Or, other question, why are leaves green?
The colour that we see is what they're absorbing. It's like the wavelength that the thing is absorbing, and all the rest, and that's back at us. Like black is the whole thing being absorbed, and white is everything being.
You are absolutely right. Yes, you are absolutely right. What we actually see is the stuff that is not absorbed. So, for example, why are leaves green? Because chlorophyll absorbs in the red and in the blue. So all the energy of red and blue is filtered out, and what's left is just green, and that is the green that we see. Was sort of what you said. Yeah. How come that in autumn some leaves are red? What's happening there? You've seen, what is called in general, what is called in the US Indian summer. Why are the leaves red? For a very simple reason. The leaves are red because the chlorophyll that usually would absorb in the red is broken down. So it no longer absorbs in the red, and instead, and it's sort of gone, and instead you have additional pigments in the leaves. This time they absorb, these auxiliary pigments actually absorb in the green. So what you have then is more or less everything is absorbed in that range, and all you have left is red. Interestingly, if you do work on flies, you can also use that, because flies can't see anything in the red. So if you want to study flies, you just turn off the light. You can't see anything, but you turn on a red light. The flies can't see it. For them, it's dark. but you can see it. Interesting things, I thought. Anyway, let's go back to what you have done or what you are doing with a spectrophotometer. Now, the point, what I'm doing, why I'm telling you all this is that, as I said, every wavelength has an associate energy level to it. And a substance usually can either absorb this energy level or it doesn't react to it. Now, when does a substance absorb? A substance absorbs a certain wavelength, a certain energy, if and only if the energy is exactly right. If the energy level is a little bit too high or too low, the substance goes, so what, not interested. So it has to be exactly right in order to do something. And what actually happens is you have all learned about electron levels, electron orbitals, and electron energy levels. And these energy levels are quite discrete. They are not sort of continuous, they are discrete. So here is an energy level of an electron, here is an energy level of an electron. Yeah, if you sort of imagine that. And in order to shift an electron from the lower to the higher level, you need to have exactly the right energy. If the energy is too high, nothing happens. If the energy is too low, nothing happens. Now, with our visible light and also UV light, we are usually working by shooting energy, by absorbing energy through electrons. But we don't have to do that. There are other options where you can have electromagnetic waves being absorbed. So, for example, if you look at how a specific nucleus, an atom in the nucleus, or the nucleus in an atom, it spins. And this spin can also be changed through energy levels, usually through radio frequency. So, if it has the right energy, the spin changes, goes the other way around. So you can modify the spin. But what you also will see is that in this case, the nucleus absorbs exactly the right energy, the right, if you like, light, although in this case it's not light. Yeah? So, why am I telling you that? What the heck? This is actually incredibly useful, this property of light and substances, or electromagnetic waves and substances, because it can help us to determine the concentration of a substance. And the premise is very simple. The more substance I have that absorbs the light, the less light will go through. So, for example, I have a container with a substance that appears red. So we see the red light. It would absorb, for example, in the green. So if I shine green light onto it, it has exactly the right wavelengths, the light. We, as I said, we measure the wavelength usually in nanometer, 10 to the minus 9 meters. And the substance will absorb some of the light, not all of it, but some of it, and a little bit less light will come out. And you can imagine, the more of the red substance I have, the more will be absorbed and the less will come out at the other end. So basically, what comes out depends on the concentration of the substance. We also have to use the right light, as I elaborated. If you don't use the right wavelength, then nothing happens, nothing will be absorbed. Has to be exactly the right one. So, if I write down our absorbance, absorbance is directly dependent on the concentration of the substance. The absorbance is also directly dependent on how much path, how long the light has to travel through this absorbing substance. So you can imagine, if I double that, still have the same concentration, but I make the path length, the active path length, where we have the substance in it. If I make this double the size, then the absorbance will be twice as large. So we can say the absorbance also directly depends on the path length. Not the length, the entire length where the light has to travel, so it doesn't matter how long this part here is before it actually hits the container. That doesn't matter. What matters is how long it has to go through the container. So this part here. Yeah? And if our substance absorbs, so what we can write now is we can already formulate a sort of a law. We can say absorbance is dependent on concentration times the path length. There's actually quite a nifty trick to get these two dependents together if I just multiply it. The higher the concentration, the higher the absorbance. The longer the path length, the higher the absorbance. And if I want to write this in an equation, I need a sort of a conversion factor. And I can write absorbance equals, instead of the direct proportional sign, equals concentration times path length. So that's the concentration. That is the path length. Times a factor, and this factor is usually abbreviated with the Greek letter epsilon. And this one is called extinction factor or absorbance factor. And basically, this tells us that this is just a factor that allows us to write this as an equation, as an equal. This extinction factor, this epsilon, is characteristic for every substance and also for a wavelength. So the extinction factor, epsilon, is, don't know why I've got a bracket here, specific for substance and that's very important, a characteristic wavelength. Now this equation that I've written down, A equals C times L times epsilon. This is also known as the Beer-Lambert Law. Because these were the guys who basically came up with this equation. So what's in it? Well, as I said, absorbance equals concentration times the path length times the extinction coefficient. And there are handbooks. Handbooks means they are thousands of pages thick, where you can look up a substance and its particular extinction coefficient for a particular wavelength. What you can do, for example, also if you want to find the extinction coefficient for a substance is you just simply take a cuvette with a given concentration and you shine light of different wavelengths through it. And then you measure how much comes through. So, for example, let's say we have a substance, don't know what the substance might be. Here is absorbance. Absorbance, and here would be the wavelength, and usually wavelength is abbreviated with the Greek letter lambda for wavelength. Let's say it's in nanometer. What we see is, for example, nothing happens because the substance doesn't absorb, and then all of a sudden we get a massive spike. And let's say this here is at 540 nanometer. We get a spike. That means this particular substance has the strongest absorbance at 540 nanometers. Yeah? Make sense? This is what I show you here is what is called an absorption spectrum. Spectrum because I shine lots of different wavelengths on it, and the absorption is how much does it absorb, basically. Right. Common mistake. People use the Beer-Lambert law, C times L times epsilon. And they are given an extinction coefficient. Oh, let's talk about units first. Let's talk about units. Because you know I have this fetish with units. Let's see whether we can work out what the different units are. So first of all, and there were questions on the group chat, what is the unit for absorbance? Well, something that I haven't told you is that the absorbance can be expressed as a sort of a ratio of two things, of transmittance in this case. And since it is a ratio, the units cancel out. So absorbance is one of the few cases where you get away not putting a unit down. So no unit, the absorbance. Concentration. What unit could that be? Loud? Yeah? Mole per liter. Or I can say molar. The path length. Oh dear, what is this? Well, the path length is how long this light has to basically travel in the substance. And that is very often given by the length, by the size of the container where you have your substance in. Usually in the lab, when you do a practical, you would have cuvettes. You've handled these cuvettes already, yeah? In the case of DNA that you used, the cuvette is made of quartz. Or did you use plastic cuvettes? Plastic cuvettes for DNA. Okay, good. I'll say something about that in a minute. And these cuvettes usually are standardized. To make life easy for all of us, usually these cuvettes have a path length of 1 centimeter. So we now can figure out what the unit for the extinction coefficient is. We have no unit equals molar times centimeter, that's the unit, concentration times path length, times, and now we need to do something so that the units cancel out. Because on the left-hand side, we don't want any unit. So our extinction coefficient would have the unit 1 over molar times centimeter. Because these units then cancel each other out and there are no units. Or you find it more commonly written as the unit for the extinction coefficient as molar to the power of minus 1, centimeter to the power of minus 1, which is exactly the same as 1 over. Yeah, that makes sense? So that is a common unit for an extinction coefficient. But of course, the concentration does not necessarily have to be in molar. It could also be, for example, gram per liter. And then it would be a different unit. So if we have gram per liter times centimeter, then in this case, the extinction coefficient would be liter per gram and centimeter. Because again, you would need to cancel it out so that you get an absorbance without a unit. Yeah? Now, so that's the unit for the extinction coefficient. Now you said you used a plastic cuvette for your DNA. And that's one of the things where a lot of experiments go wrong, because What was the wavelength that you used for your DNA sample? 200 and 260, 250? So you did 260 and the 280. Yeah. What was the 260 for? That was the DNA. Yeah. 280 was? Sorry? Protein. Yeah. So 260 nanometers. Did you see the light? I saw the light. Did you see the light that goes through it? No, you can't, because that is pretty much 260 nanometers is way in the ultraviolet light range, so you wouldn't be able to see it. And about 10 years ago, you would have to have special cuvettes for that. Actually, you had special cuvettes for that, because a normal plastic cuvette would absorb very nicely ultraviolet light. And if the cuvette absorbs it, then no light would go through, and the whole thing would, be totally pointless of measuring it. One way to deal with that is to use substances that are actually translucent for ultraviolet light. For example, quartz, mineral quartz. Quartz does not absorb at 260 or 280 nanometers. And therefore, people used to work with these little quartz cuvettes, which were prohibitively expensive. Glass would not work, because glass, like ordinary plastic, would absorb UV light, and therefore can't be used. People have now manufactured different kinds of plastic that do not absorb ultraviolet light, and therefore you can use these special plastic cuvettes. They are slightly more expensive than the normal cuvettes, but you need to use them, because otherwise your light, your ultraviolet light that you are trying to shine through your substance, would be absorbed just simply by the material of your container. And that's not what you want. You want it to be absorbed by your substance, but not by the container. Make sense? Now, frequently you run into a problem because Sod's law, nobody knows exactly the extinction coefficient for the substance under the particular conditions that you want to measure. Bam! What can you do? Well, in this case, what you can do is you can say, right, I take my substance, I use known concentrations of my substance, and I measure the absorbance for it, for each concentration. So what you do, and that is something that we are going to do in week 8 in the assessed practical, you have, for example, a protein, and you have a concentration of the protein. For example, in milligram per liter or something like that. And you simply measure the absorbance. And what you find is, up to a certain point, you find a linear relationship. It looks a little bit like that. It's not because I can't draw a straight line. We'll come back to the curve in a moment. What it basically tells you is that if I have a certain concentration, let's say I have this concentration, like let's say 5 milligram per liter, I get a particular absorbance. If I have 10, I get a particular absorbance. If I've got 15, I get a particular absorbance. And this thing is actually called a standard curve or calibration curve, this graph. You will draw loads and loads and loads of standard curves in your life as a scientist. It's very common. And all you need to do is really you need to use this standard curve to identify the concentration of your protein, like you would do with the Beer-Lambert law. But you use the standard curve if you don't know the extinction coefficient. So for example, if you have an absorbance of, let's say, that much, you just simply use your standard curve like that and say, aha, this is here where it hits the standard curve, and my corresponding concentration is this one here, probably around 14 milligram per liter. So this is quite a nifty trick. If you don't know the extinction coefficient, however, if you've got something like that, you can easily calculate the extinction coefficient. Because you've got absorbance, you've got a concentration, you've got the path length, 1 centimeter usually. So all you need to do is you just simply rearrange this equation here and rearrange it for your extinction coefficient. Extinction coefficient equals absorbance divided by concentration times path length. So you can very easily, once you've done that once, you can easily calculate your extinction coefficient. But very often it is more convenient just simply to use a standard or a calibration curve and straight away read off what your protein concentration or what your concentration is in this case. Make sense? Why did I draw it like sort of plateauing off? Just simply because your spectrophotometer usually can't deal with absorbances higher than 1. So anything higher than, let's say, an absorbance of 1.0, here the relationship is no longer straight and linear. It does all sorts of weird things. So very, very important, do not measure absorbances higher than 1. So question for the quick. You measure an absorbance of your substance, you measure an absorbance of 1.4. What should you do apart from cry? You dilute your substance, you dilute your sample. You can dilute it, with the same amount of, let's say, water or some other components. Make sure that these other components don't absorb the light. Yeah, that's very important, because if you dilute it and that adds to your absorbance, then you are measuring total nonsense. Yeah, bless you. Dilute your sample, measure again. And do that as often, and do that so that your absorbance, your final absorbance, will be definitely below 1. If you go over 1, you just as well just pick some random numbers. They will just be exactly the same. Make sense? Yeah? So now you know how basically what it is that you've done in your practical when you measured the absorbance. One last thing about that. Very often, especially with final year students, and I hate to say that, very often you see that these final year students say, right, I have wavelength 700 nanometers, I have an absorbance of 0.6, and I have a wavelength of 1, and my extinction coefficient is 100 per molar and centimeter. So in order to calculate what was the Beer-Lambert? It was A equals C times L times the wavelength times, there's an extinction, don't know what this extinction called, I will just leave it. No. The wavelength will never ever make its way into the Beer-Lambert equation. Absolutely essential. The wavelength is included in the extinction factor, in the epsilon, but it will never ever, under any circumstances, show up in this equation. If it shows up, you will see red dots on your exam paper. And you know that these red dots, you only see them because it absorbs anything green, anything good. Right? So that is wrong. No wavelengths. The wavelength is in the extinction factor or coefficient, but not in the equation. Does it make sense? Good. 5-minute break, and then we move on to pH. You've done that at school? No? You've done that at school? A bit of it. Just a bit. Good. So it was something new. Absolutely. It's live streamed.
Okay.
So, and it's recorded.
Okay.
So if you don't come back, no problem.
I just wanted to ask, when to convert grams per litre to moles per litre, you have to divide by the amount. No.
You need the molecular mass.
Okay, so this is divided by it.
Yeah.
Okay, cool. I was just confused for a second there.
Have you done that stuff at school?
Bits of it.
Bits of it.
Not Beer-Lambert Law.
Okay.
Obviously, like absorption concentration kind of things like this one earlier.
Okay. So it was some of the stuff was new. My worst nightmare that I bore you by telling you stuff that you've long forgotten.
I need lots of like refreshments.
Oh, refreshment. Yeah, I would like to have refreshments.
Yeah.
We should order them.
Yes.
So when we have these values, we don't do that for the needs. Then when we rearrange it, we feel like it's going to go on C.
We usually want to find C.
Yeah, usually. If yeah, then that's is that the right read?
Yeah.
Wait
a moment. Yes, that's absolutely right.
So
Yep.
there I got 60. So concentration is 60 per
Yep.
milligram mole.
Absolutely.
Thank you.
Okay. Let's get back. I've just seen somebody asked on the group chat or made a comment in the group chat that when you measured your DNA at 260 nanometers, there's also the problem that the amino acid phenylalanine absorbs very easily at 260 nanometers. So how can you discriminate? How can you tell which one is which? And isn't there sort of a contamination? Yes, absolutely. And you will find very often that you have different components in your solution that all absorb at the same wavelengths. And then you are totally screwed. The way you can deal with that is these substances all probably have different intensities at which they absorb wavelengths and different peaks where they absorb. So you can measure different wavelengths and you can set up a lot of sort of simultaneous equations. You can say at the wavelengths of A260, I have a contribution from phenylalanine and from DNA. At an absorbance of 280, I have a contribution of tyrosine and DNA, a little bit, but not so much. And from that, you then can calculate what each substance contributes to the absorbance, and you end up with a total mess of equations, which is also known as multi-component analysis. It drives you insane, but luckily clever people have written computer programs where you just can add your numbers, put your numbers in, and it tells you how much of each component with a given extinction coefficient are present in your solution. So I would not expect you to do that, but just to say it's a very valid point that you can have substances that are very similar or identical in their absorbance, in their extinction coefficients. Right. Let's move on to a slightly different topic, although you might find that a substance can have different extinction coefficients depending on whether it is in a certain acidic environment or in a neutral environment or in a basic environment. And that brings us to acid and bases. Acid, bases, pH, pOH. I assume for most of you this is just pure revision. Hands up who feels confident with acid and bases. Hands up. Quite a lot of people. Who feels a little bit shaky with that stuff? Hands up. Acid, bases. Few people. Okay. So very brief revision. An acid, under the conditions that usually we are dealing with, is just simply defined as a substance that can donate protons. And I write that as HA usually gives a proton and A minus. So in this case, HA, it has a proton attached to it, and it can give off this proton. So therefore, this HA would be classified as an acid. That's the classic acid definition from a guy called Brønsted. Over 100 years ago, came up with this definition. An acid is a proton donor. There's another acid definition. An acid is also could be defined as Louis? No? Don't do that? Louis? Definition? Here is a substance, iron 3 chloride. Iron 3 chloride is actually a strong acid. And you will say, WTF? Why is that an acid? It doesn't have a proton in it. Well, what actually happens is that this substance, iron 3 chloride, grabs a water molecule, and in particular, it grabs an electron pair. And what happens in this case is you get FeCl3 OH, and the whole thing is negatively charged, plus a proton. Hey, look, there's our proton. In this case, it does not come directly from the iron chloride. It comes from the water, but the probably more modern definition of an acid is an electron pair acceptor. You probably will come across that when you do a little bit of organic chemistry in phase 128 or so. Sorry? No. Well, you use, for example, substances like iron chloride or aluminum chloride to catalyze certain reactions where this as an electron pair acceptor comes into place. So, however, we only work in an aqueous system, and therefore we get, and now here the thing is that usually we don't have naked protons sitting around. These protons are always sort of encapsulated with water surrounding them, and very often people write them as H3O+. This just means it is proton plus water. And it does not mean that this proton is just surrounded by one water molecule. I think nobody really knows how many water molecules are surrounding a proton, and probably this number can also vary dramatically. So it could be H201 O100 plus. So let's not worry about it. Very commonly it is written as H3O plus A minus. And as I said, this guy is an acid. Now, if an acid is a proton donor, and with proton I mean H+, proton donor, exactly the opposite is true when we are talking about a base. A base, therefore, is a proton acceptor. So the acid gives off the proton, and the base would happily receive the proton. So, for example, we have, as an example for an acid, we've got HCl, and this almost completely breaks down into H plus Cl minus. base, we might have NaOH, sodium hydroxide. This breaks down into Na plus OH minus. And this OH minus, if there is a proton around, it will grab the proton. So, for example, if we add a proton, it will grab the proton and it will produce water. So here, the NaOH, the OH minus, that would be classified as a base. Yeah? Make sense? Here comes sort of a little bit of mental gymnastic, mental yoga. Let's say we have HCl we can write this as H plus Cl minus. Right. Which one is in this equation? And I've written it so that it goes in both directions. In this case, it's probably not exactly true because HCl, as I said, almost totally disintegrates only into H plus and Cl minus. There's usually not a lot of going back in the other direction. But for our purposes, let's assume it goes back. Which one is the acid? HCl, that is the acid. Absolutely right. Does this equation, this chemical equation, contain a base? Yeah. Yeah? Where? Ah, you're absolutely right. There is also a base in it. This Cl minus could be classified as a base. Why? Just simply because it can accept a proton and move in the other direction. Does it make sense? So you have an acid. The acid disintegrates into a proton and the corresponding base. Now tell me, what is the difference? What is the difference between the acid and the base here? What's the difference? It's plain obvious. There are two differences. In this case, the difference is one proton. HCl has one proton more than the corresponding base, Cl minus. Yeah? One proton, only one. And the other difference is charge. While the acid is uncharged, the base is negatively charged. Okay? Now, if you have a system where you have exactly this, where you have the difference between the acid and the base, where this difference is only one proton, this has a special name. This is called a conjugate acid-base pair. Please remember that because we need that for next week. A conjugate acid-base pair. Right. Now, let's have a quick look at a general equation. We can write HA plus water gives us, and I write it like that with this double arrow. This double arrow means it can go either direction. And we are basically at a point where a chemical equilibrium has been established. We will discuss equilibria when we come to kinetics, probably shortly after Christmas. So here we have H3O plus OH minus. Right. Oh, sorry. Oh, God, that's going too fast. A minus. So, HA, what is it? Acid. What is H2O? Water. Yeah, I know. What is it? It's a base. It's a base because it accepts the proton from the HA. H3O plus, what is that? Ha! This is now the acid because it can give off a proton. And the A minus is the base. Are you happy with that? Make sense? HA and A minus are conjugate. What about H2O and H3O plus? Are they conjugate? Yes or yes? Yes, because the difference is only one proton. H2O plus H2O gives H3O plus plus OH minus. Which one is conjugate? Or let's have a look at it. There's something weird going on, isn't it? In this case, the water can act both as a proton donor and a proton acceptor. So it has amphiphilic properties. It can act as both an acid or a base. Question. H3O plus and OH minus, are they conjugate? Are they conjugate? No. Why not? Because the difference is 2 protons. So they are not conjugate. That's very, very important. Right? Now you're all familiar with the fact that we very often want to measure our proton concentration in a solution. So proton concentration, that is something that we very, very often do. And we have little electrodes that we can just stick in our solution, and it measures the concentration of protons in the solution. And this is the readout from these electrodes is usually given not as a concentration, but as a value, which is called pH value. pH value. I'm sure you all have heard about pH values, yeah? Right. In water, or I probably should say, what is a pH value? pH value is defined as pH equals the negative logarithm to the basis of 10 of the proton concentration. Negative logarithm base of 10, usually we don't write the 10, of the proton concentration. And here the troubles start. What is the unit for the proton concentration? What would be the unit for that? Sorry?
It's a logarithm.
Good man. Good man. The unit for proton concentration would usually be mole per liter. Or molar. Yeah? But I told you in one of the previous sessions, you can't have the logarithm of a unit. It just simply doesn't make sense. So the definition is the pH equals the negative logarithm to the base of 10 of the proton concentration measured in molar. That's very, very important. It always have, and the understanding is it is always molar, mole per liter. Right? So, let's do a quick calculation. Let's say I have a 0.1 molar proton concentration, H+. Let's calculate the pH for that. pH equals negative log of 0.1, and I should probably say molar, but I can't really write it. Yeah, I just have that as sort of as a aide memoir. But it's in molar, and that's good. So what you can do now is you can put that into your calculator. And you should get, for that, a value of 1. How does it work, actually? Well, you have your proton concentration, 0.1 molar, and that is the same as 1 times 10 to the power of minus 1. True? With a logarithm, you actually find the number that is up here. That is what a logarithm actually does. So the logarithm to the base of 10 of minus 1, of 10 to the minus 1, gives you minus 1. And for the definition of pH, we also have a negative sign here. So log of 0.1 gives you negative 1 times minus 1, that gives you 1. Does that make sense? Let's say we have a pH. We want to find the pH of a solution that is 300 millimolar. Oh dear. Oh dear. What do we do with that? We actually need to convert the millimolar into molar because otherwise we could not do a pH. Remember, pH needs to have molar in it. So that gives us 3 times 10 to the minus 3 times 10 to the minus molar. Sorry? 3. Are you sure? 300 millimolar? How much? 2. Minus 3. 3 times 10. 0.3. I think we need to do another workshop, hey? What is 300 millimolar? It's 0.3 molar, right? Isn't it 0.3 molar? 300 millimolar? So it would be 3 times 10 to the minus 1 molar. Or I could write it as 300 times 10 to the minus 3 molar. It's the same thing. Yeah? So what I need to do is, I need to calculate pH equals minus log of 3 times 10 to the minus 1 and that's in molar. Can somebody quickly do that? Thank you. 0.53. 0.52. Good. Let's do it like that. So the solution would have a pH of 0.52. What's the range? What's the pH range usually? Some of you have done that. What's the pH range that we usually deal with? 1 to 14. Have you ever watched IQ on telly? The program. Yeah? So, pH range 1 to 14. Mac! Wrong answer. Not wrong answer, but actually, let's try again. Can we have a pH of 0? Yes? When? Sorry? Oh, Alex has a really good suggestion. When there's no proton in it, do we have a pH of 0? No. Oh, we have a pH of 14. Oh, that's interesting. Okay, let's try Alex's suggestion. Yes, we try. No, it's a good suggestion. It's a very good suggestion. Let's say our concentration of protons is 0 molar. Proton concentration equals 0 molar. Let's calculate the pH. pH equals minus log of 0, and we have it in molar. Can you try to do that with your calculator? What do you get? A math error. Actually, you can't calculate the logarithm of 0. Not possible. Can you have a negative concentration? Yes, a negative concentration. So a substance has a concentration of minus 5 millimolar. That would be interesting, actually. I guess you could have that, but only on the engineering deck of the HSS Enterprise. It would be antimatter. Doesn't matter, but you know, antimatter. You can't have a negative concentration of something. Doesn't make sense. Either it's there or it's not. Either you have a concentration or not. So negative concentrations are out. Now, when can we have a pH of 0? Because some people of you said we can have a pH of 0. When it is 1 molar. Ah, that's interesting. How did you do that?
I guessed and checked it on my
You guessed. Ah, okay. Okay, let's take the guesswork out of it. Let's take the guesswork out of it. Right? We have a pH. pH equals 0. What is the corresponding concentration? You are absolutely right, yeah? But let's take the guesswork out. So we said pH is defined as negative log of the concentration. And I'm just simply too lazy to write the 10. It's always, by definition, it's log 10. Log concentration, negative log concentration, equals 0. So how can we actually solve this equation? First of all, let's get rid of this nasty negative sign. So we can multiply both sides by -1, and we get log concentration equals -0. Doesn't make any difference. 0 is 0, but I just brought this negative sign to the other side. Yeah? Now we have still this yucky log sitting there. And remember, in the maths workshop, I told you that the inverse mathematical operation to addition is subtraction, to multiplication is division, to 10 to the power of, the inverse operation is log. Or the inverse operation to log is 10 to the power of. So what I need to do in this case is both sides of this equation I take 10 to the power of. On the left-hand side, I get 10 to the power of log concentration equals, and I need to do that on the right-hand side as well, 10 to the power of 0. Since it is the inverse mathematical operation, 10 and log cancels out, the concentration falls down, and all I have is concentration equals 10 to the power of 0. And we know that anything to the power of 0 is 1. Ah, wait a moment. We have a problem here. What's the unit? Loud? The unit is molar. Absolutely right. The unit is molar because that was inherently in here, in the concentration. So, yeah?
What's happened to the minus? Does that not carry through?
What minus? I just dropped it because -0 or 0, but you're absolutely right. It should be there. Yeah. So you now can calculate what is my proton concentration if I've got pH equals 3.0. What is my proton concentration in this case? Try it. What's the proton concentration? Obviously, you need to familiarize yourself with a calculator. You totally got it. So you have minus log concentration equals 3.0. We want to know the concentration, so we take both sides 10 to the power of. We have 10 to the power, oh, sorry, no, we don't do that. First, we bring the negative sign to the other side. So we have log concentration equals negative 3.0. And in this case, I can't drop it. Now, we take both sides 10 to the power. 10 to the power and log cancels out. So we've got concentration equals 10 to the power of minus 3.0. And if you put that in your calculator, this gives you 0.001. What? Bananas? Molar. Or I can write this as 1 times 10 to the minus 3 molar, or I can write this as 1 millimolar. Happy with that? You can convert proton concentration into pH and pH into proton concentration now. Okay? You need to practice, but practice is on my calculation website. Right. Let's do another calculation. I want to know the pH of a very dangerous substance. Actually, this is the most dangerous substance on this planet. It's called dihydromonooxide, which is water. Water. It's the most dangerous substance. Every year, thousands and thousands of people are killed by water. Flooding, drowning, all these things. So, what is the pH of water? Sorry? 7. It is 7. Somebody says 7. You're absolutely right. pH of water, of pure water without anything in it, pH of water is 7. What is the proton concentration? What's the proton concentration of water? Loud? Sorry? You're absolutely right. So, Alex just said, the concentration of protons, so proton concentration, and very often this is abbreviated with these square brackets. Proton concentration of water equals 1 times 10 to the minus 7 molar. Yeah? Happy with that? Remember this value. Where do the protons actually come from in water? They come from another water, or they come from water. So if you like, you could write H2O dissociates into H plus OH minus. This is where the protons come from. What is the concentration of OH minus in water? Sorry? What's the concentration of OH minus in water according to this equation?
It's 1 times 10 to the minus 7 molar, just like proton.
You are absolutely right. It is 1 times 10 to the minus 7, just as the protons. Why? Look, I have my water. I split that into protons and OH minus. So for each proton that I get, I also get an OH minus. True? So in pure water, I can say my proton concentration is the same as my OH minus concentration, equals 10 to the minus 7 molar. They're both exactly the same. Now, one thing that we can also do is, instead of calculating a pH, we can calculate a pOH. And you don't need to be a rocket surgeon to figure out what that is. It is the negative log of the OH minus concentration. In molar again. Hey, how cool is that? So for water, I can say pH equals 7, pOH equals 7. It's exactly the same. Both are the same, 7 and 7. Now I can add up pH and pOH. pH plus pOH together gives us, loud, 14. Hey, cool. This is where your 14 comes from when you said the pH range goes from 1 to 14. Actually, it doesn't. It can go down to 0. It can go way above 14. Can a pH be negative, by the way? Yep. You say that so convincingly. pH can be negative? Absolutely right. If you've got, for example, a 10 molar solution, negative log of 10 is negative log of 10. What's the log of 10? 1. Negative log of 10 is minus 1. So a 10 molar solution would have a pH of minus 1. Make sense? So if you say the pH range goes from 1 to 14, no, it can be anything, whatever you want. And we have the relationship pH, at least in water. For other substances, it's different. In water, we have the relationship pH plus pOH equals 14. Yeah, you might say, Master, that's all well and good, but we are, usually we are not dealing with just simply water. I might have an acid in it. Let's just simply quickly do that. We have HCl plus water. We know what that does. It gives us H3O plus Cl minus. Acid base acid. Oops, that was the wrong one. Sorry. Base. Now, HCl is a very, very, very strong acid. Strong acid actually means that this acid totally dissociates into the protons and the Cl minus. Strong acid equals total dissociation. Okay? And another thing that I need to point out to you, that's something that you've done for your GCSE, so a long time ago. If you have an acid, the pH is always lower than 7. At least in water. For an acid, the pH is always lower than 7. Yeah. So, of course, what we can do is we can now say, right, we, instead of working just with the water thingy and with a fictive substance, we can say, what about we are working with, let's say, a 0.1 molar hydrochloride solution. 0.1 molar hydrochloride. And we want to figure out what is the pH of that. Now we can say, we know hydrochloride is a very, very strong acid. So if I start with a 0.1 molar concentration of hydrochloride, I end up, it completely falls apart. I end up with 0.1 molar protons plus 0.1 molar chloride ions. Because it totally falls apart. can you calculate the pH of this 0.1 molar hydrochloric acid? What do you think is the pH? On your calculators, if you need one. pH equals 1. So the pH of a 0.1 molar hydrochloride solution is 1. Did you see what I sneakily did? Instead of asking you to calculate the proton concentration that you have done, I ask you to calculate the proton concentration, the pH, from the acid. And you could do that simply because you knew that in this case it's such a strong acid, the proton concentration equals the acid concentration. And I write that in shorthand like that. Every single molecule of hydrochloride or hydrochloric acid will break down and give me the same number of protons. Make sense? Right. Let's do a little cliffhanger with you. I have my HCl concentration equals 10 to the minus 5 molar. (10 to the minus 5 molar. What is the pH? What's the proton concentration? Loud? The proton concentration, absolutely right. The proton concentration is 10 to the minus 5 molar. So what's the pH? Loud? 5. So pH of this concentration of hydrochloric acid equals 5. Yeah? Happy with that? Don't hit him, even if he deserves it. I'm not saying that he does, but he does, okay. Right, now, here comes the cliffhanger for you. I have a proton, I have an HCl concentration equals 1 nanomolar. One nanomolar. How many moles is that? Mole per liter. One nanomolar is 1 times 9, 10 to the power of minus 9 molar. Calculate the pH, please. 9. pH is 9? pH is 9. Okay? It was easy. Remind me, what is HCl? What is it? It's an acid. We said an acid always has a pH smaller than 7. You just sold me hydrochloric acid with a pH of, what was it? 9. Very clearly, pH of 9, that would indicate it's not an acid. Do you see my problem? Do you see the problem that we have? Solution next week. Have a lovely weekend.